Hello and welcome to TidyX episode 97. TidyX is a screencast where we go through and explain how our code works. My name's Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name's Patrick Ward. You can find me on Twitter at OSPPatrick and at tidy_explained is where we both live on Twitter, and tidy.explained@gmail.com is where we both live in the email world. And you can always go to our GitHub repo and open up an issue, or best way probably to get in contact with us, and seems like everybody's favorite way, is like and subscribe on the YouTube channel. We also have a Patreon page, and we really appreciate everybody who's donated to us. We love doing the work, and we're glad to see that other people love doing the work and want to support it in some way. We drank all of the money that was donated so far. So if you
we need more supplies.
are watching this, we need more provisions. So if you're watching this and you enjoy what we do and you'd like to buy us a coffee or a beer, we will gladly accept that, and we appreciate
support
it.
Local Seattle.
Yes. This is local coffee, local brewery. That's it. There you go.
All right, so now we're done with our intros. Once again, thank you so much to our patrons. We're going to be starting a new series. So last week we ended our series on R Markdown, so hopefully y'all found that valuable and interesting. We're going to be starting a new series now on sampling, simulation, and an introduction to Bayes. So that is a heady, big topic right there. I feel like
a lot going on.
We've been working in R for a while doing that. I mean, we've been working in R traditionally, that's statistics. We've been focusing on a lot of other non-statistical type work because R does a lot of things really well. But now we want to go in and focus a little bit on a little bit of statistics and try to make it really accessible for y'all. So I will share the screen as Patrick can give a little spiel about what we'll be going over.
Yeah, we've done a few bits of simulation, and we did some NHL hockey stuff. We did some Bayes stuff when we talked about the volleyball players way back, probably like episode 17 or 22 or so. I mean, it's a long time ago now. So we want to take some time and actually dig through some of the functions and the features of that stuff and maybe make it a little bit more approachable or accessible, as Ellis said. I think what you'll see here in my code is that while we've done like 97 episodes, pretty much all of them heavily tidyverse syntax, a lot of times when I'm doing this type of work, when I'm doing a lot of Bayes modeling type of stuff, I am using base R because I'm working with like vectors of data and things like that. And so we're gonna use a lot of base R, and I'm sure along the several videos in this sample, I will have a bunch of base R, and then Ellis will go, oh, that looks like crap. We can do this in tidyverse, and then he's going to make it look prettier, and then everybody's going to learn a whole bunch of cool stuff. So we're gonna kick this off by explaining simulations and distributions in R. So we'll load up some packages here. We'll load up tidyverse, which we'll use some ggplot in a little bit, and GT for some tables. And the first thing I want to say is that R does an awesome job of providing us with very simple functions for creating distributions. So we don't have to do a lot of the internal math and write the functions ourselves, right out the math. So how does it work? R has these cool distribution functions that basically take a prefix, and then that prefix defines what it is from the distribution that you want. So in the case of P, it'll be a cumulative density function. In the case of D, it'll be a probability density function or a probability mass function, depending on whether it's a continuous or discrete outcome. Q will be a quantile function, and then R is going to be a random draw. And I'm not going to get too in depth on those right now because you're going to see them in the examples.
And it's much easier to understand it when you actually see it.
Way easier than me talking through it. The prefix is followed by a suffix, which describes the type of distribution that you want to work from. So as you could imagine, these are all named very conveniently. Norm is going to give us a normal distribution, binom, a binomial, Poisson, or Poiss, a Poisson, EXP, exponential, UNIF, uniform, beta, beta, et cetera, all the way down, T distributions, F distributions, chi-squared distributions, log normal distributions, all of those types of things. The only thing you have to pass, you give it a prefix, you give it a suffix, and then within the arguments, you're going to generally pass the parameters of that distribution. So just very simply, a normal distribution has two parameters, a mean and a standard deviation. A binomial has two parameters, and n samples and a probability of success or failure. Beta distribution, alpha and beta. Poisson has a shape and a rate parameter. So we're going to go over these very specifically now, and then we're going to build them up into one big simulation to kind of use a whole bunch of them all at once stacked together. So let's give some examples of where you might use this. First one is, let's just create a random draw of 10,000 points with a mean of 0 and a standard deviation of 1. You can set the mean and standard deviation to whatever you want it to be. R is automatically going to default to a mean of 0 and a standard deviation of 1, which makes this very handy if you're building models. But of course, mean and standard deviation could be whatever you want. So in this case, I'm passing n equals 10,000. I'm using scientific notation here because I was being lazy. And then we get a cool basically a vector of 1,000 data points, all of random samples coming from a mean of 0 and a standard deviation of 1. And so what can we do? We can plot this and we can look at that distribution, get an appreciation for the density of that distribution around the mean and how it fans out into the tails. We could also plot this as a density. So we use plot and then we pass the density function inside of plot, and we put our distribution in there and we get this nice looking density of data. Great.
Huzzah.
Okay. So that's our norm.
And it looks normally distributed. What do you know?
Exactly. And the best way to learn this stuff is to literally play with all the distributions and feed them numbers and see what they look like. All right. So let's talk about cumulative density. In a normal distribution with a mean of 0 and standard deviation of 1, we want to know what is the percentage of data that's below a specified value. So what if you're 2 standard deviations out in that distribution to the right? What if you're 1 standard deviation? What if you're right in the middle? Or what if you're below the middle? What if you're 1 standard deviation below the mean? What's the probability of data below that? So here we use Qnorm, and so we're going to say, if I look at Q equal to 2, so if I'm 2 standard deviations out on a distribution with a mean of 0 and a standard deviation of 1, how much data is below that? And if we run that, we get this back and it says about 98% of the data is going to be below that point. So 2 is in like the 98th percentile. There's all this data below it. And R is always going to default to lower tail equals true, which is important to keep in mind when you're doing this, because if you want to know the probability of data above that point, you either have to do 1 minus Qnorm, or you can take the inverse by doing lower tail equals false. And so if we feed that, we should get 0.0227, which is 1 minus 0.99977, right? So we get the inverse. And so we can do this for any of those values. If we're 1 standard deviation out, how much data is below 1 standard deviation? 84% of the data. 0 is going to be 0. Like that's your sanity check. It should be right in the middle, 50-50. And then negative 1 standard deviation will be the inverse of 1 standard deviation, right? It's like the opposite. And then.
So to be clear, Q is not actually standard deviations. If the standard deviation was 2, this would still stay 2 because this is at value 2. Right?
Yeah, correct.
It just happens because standard deviation was 1.
Yes.
If we wanted to know 2 standard deviations above it, they're equivalent.
Yes, good. That's a good point. Q is the point that we're inquiring about within our known mean and standard deviation. Correct. Yeah. So we could plot this with our line at 2 standard deviations out. So we're basically going to plot the same distribution that we created in our norm. And that's going to have a mean of 0 and standard deviation of 1. And then we can plot our little line here. And so we're going to stick this right at 0.2. So remember, Q is 0.2. And so there we see 97.7% of the data, 0.977 is going to be contained below that point, and then we can see the inverse, which is that small little 0.0277 is above it. Yeah, pretty cool. All right.
And that's
moving
how
on.
Qnorm worked, which
that's how
this
Qnorm
explanation,
works.
when we were going through this before we recorded, I never really understood Qnorm. When Patrick explained, I was like, light bulb. Don't know.
Hopefully hopefully others have the same light bulb moment there. Yeah, right. Okay, let's look at dnorm. So this is a density function. So what's the probability of 5 successes in 16 attempts if our probability of success is 50%? Okay, so as I said before, D is the prefix that is explaining the probability density or the probability mass. If the outcome is discrete, it's binary, it's a count, 0, 1, 2, 3, 4, 5, 6, or it's groupings, group A, group B, or group C, we're dealing with a probability mass. What's the probability of the mass of the data within each of those discrete buckets? If the outcome is continuous, like that normal distribution we work with, we're dealing with a density function. What's the probability density, the area under the curve within a specific region of that distribution? So here we're dealing with probability mass function, and we're going to use dbinom to say, hey, how much probability is there of seeing 5 successes in 16 tries when our probability of success is 50%? So if we run that, we get the outcome, which is right around 7% chance. And we could change P. So let's say the probability of success is 95%. So if we went up there and we said, what's the probability of 95%? And extremely
very unlikely.
Yeah, very unlikely. There you go.
That you'll only have 5 successes if 95% of the time you're expecting a success.
Correct.
Right. That is my grokking of that.
And yeah, there you go.
There you go.
And we could do same deal here. What's the probability of flipping an even coin and getting a single head, only a single head in 20 flips with a 50-50 chance? So obviously we would expect many more heads if we had a 50-50 chance than just one.
Yes.
But it's not impossible. It's just improbable. Okay. And now we'll use our Qnorm functions and our Qt functions. So we're going to pull 95 percentile or quantiles from a normal and a t distribution. So if we look at that to the right, we look at that distribution, that density. What we're asking for here is tell me how much data is contained, the area under the curve of the data when there's 95% of that inside of that distribution. So we have 5% on each side. So if we did 1 minus 5%, we have basically to shave off 0.25% on each side. So that's why we have the P is equal to 0.025 or P is equal to 0.975. We have a mean of standard deviation, a mean of 0, standard deviation of 1. And when we run this, we get 1.95 and 1.96, right? If you've ever built confidence intervals, those are the general recommendation of the Z critical value. Now, if we have a small sample size, and usually stats books are going to say anything like 20 or 30 is considered small, we would, instead of using a Z value, we would use a T value or a T distribution. A T distribution resembles a normal distribution, but it just has much fatter tails to account for the uncertainty, to account for the fact that we have a smaller data set, we have less degrees of freedom, we have less information, and so we don't want to be too bullish. Mm-hmm. And so what you'll see here is if we have only 30 observations, our degrees of freedom is going to be number of observations minus 1, and we look for that 95th percentile or quantile, the innermost data is contained within -2 and 2. So you could see how much wider that is than the normal distribution. And so now we can actually look at like, well, how does T change when we have larger samples? So what you'll see is we have samples of 30, 70, 100, and 1,000. Once we get to 1,000, it now resembles what we saw with that normal distribution. But you can see how it's this slow kind of walk down as we get more information. We're more confident about what we're looking at with regard to the distribution and where those points fall and how much data is contained on the inside of that distribution. And so we can plot this. So I'm going to use the curve function to plot the density DT. So we're using a T distribution. And we have 5 samples, 30 samples, 100 samples, 1,000 samples. And we're going to plot from basically -3 to 3 standard deviations out. And we're going to create these kind of cool lines. So if we do this one by one, what we'll see is we'll see the shapes of those distributions shrink. So there's the red one. That's only 5 observations. If we run the next one with 30 observations, it gets more narrower at the peak and the tails get smaller. Then the blue one is a little higher than that. And then the orange one a little higher than that. So as we build up observations, we start to have a better sense for where the distribution lies. Okay, so that's kind of an intro to some basics on distributions in R and the functions that produce them. So what can we do with these functions? All right, let's go through an example. We can build simulations. So why do we create simulations? This is one of my favorite things to do. It helps us understand variation and randomness in the world. The statistical models are not deterministic. So just because it says there's a high chance of Y happening, it doesn't mean that it's always going to happen. There's some variance around this and there's some uncertainty around this. So simulation can help us with that. It can also help us with making inferences to broader population. We don't know the entire population of the Seattle area, but we might have a sample of 40 people. And we don't want to be too bullish on that sample, but we want to account for the fact that there's some uncertainty in it. And then we can create many samples of data and assess their patterns. So this is really cool because you can tweak things and see how the world might change given other assumptions. And that's really where simulations can help you out. So let's build a fun simulation. We're going to use linear regression here. And we're going to get some lahman baseball data. And we're going to use batting data. And we're going to get seasons 2014 and seasons 2015 of all players that had greater than or equal to 250 at bats. And we're going to calculate their batting average. And we're just going to keep the player ID and the batting average because that's all we care about because we've specified the sample size of players that we're interested in. And we're going to merge these together. And now we'll have a single data set. And from this data set, what we're curious about is that column 1 represents the 2014 batting average for the player. And column 2 is the 2015 batting average. And what we want to do is we want to try and predict column 2. We want to try and predict 2015 from 2014. And you can see just by even eyeballing the first 6 rows, there's some variance there, but they're all within a certain band of information. So first thing before we build the regression, we'll just plot a little correlation here. We'll do a correlation test and we find that R is equal to 0.42 and we have some confidence intervals there. Again,
so width is an interesting function too. I just wanted to say
yeah.
Width allows you to apply a function. It makes it act like tidyverse, where it
Correct.
says with this data, I'm going to apply core test on these 2 columns within dat.
And if we didn't use width, I'd have to do dat $BA 2014, dat $BA 2015. So width is another lazy shortcut.
It's a shortcut. No,
yeah, it's a shortcut.
I just wanted to make sure people were understood what that was because I don't think we've used width a lot.
No, yeah, and I do use it a bunch. Really useful. So we'll build our regression model. Again, we're predicting 2015 from 2014. There's our coefficients. We can run summary and we can see the estimates, the beta coefficients with an intercept of 0.148 and a slope of 0.433 basically, and our residual standard error, et cetera, et cetera. We've gone over these before. So what are we going to do with this? We're going to use this regression equation and we're going to use it to basically explore the uncertainty around the slope and the intercept. So first, let's just get a plot of our data with that regression line using the slope and intercept. So we plot 2014 and, first we have to make the prediction. So if we get a value of predictions, basically this is the data. We're basically using predict to say, predict 2015 from 2014. And so we get this vector of predictions. We're going to make a plot then of the data. So this is 2014 on the x-axis, 2015 batting average on the y-axis. And then we're going to use the AB line and we're going to pass it our actual model. So it's going to do the heavy lifting here, and it's going to pull the slope and intercept out for us. And there we see this red line, and that's the regression line. That's the prediction line. And the points are randomly distributed around that line. And the difference between each point in that line represents the residual of the model, the residual of the prediction. So what we want to do is we want to account for the uncertainty, because that red line is really one line of many potential lines that could have been produced from this data. And so here's how we're going to do that. We're going to build a simulation. So the first thing I do, I'm going to set the seed so that our results are replicable for you. We're going to run our simulation 1,000 times. You can work with different, you can jack this up to 1,000,000 times. It doesn't matter. You can jack it up, you can downsample it to 100 times. It doesn't matter. We're going to do 1,000. We're going to do 1,000 simulations. And I'm going to set this little parameter estimates matrix. And this matrix is basically right now NA, but it's going to collect each observation from the sample, from the simulation, and store them in column 1, which will be the intercept, and column 2, which will be the slope. Our model coefficients, we're going to actually pull from the model that we built. So remember, the model is called fit. And if I use coefficients and I use just some matrix text here, I'm pulling out 1, which is from that single vector, and then I'm pulling out 2, which is the slope. And then the RSE, if we run summary over fit, the RSE is the sigma. It's the model error. And so it's pulled out right there, point in the bottom chunk there. Yeah, residual standard error, 0.02698. That's what we're going to use. And then the sample size of 100 here is basically, we're going to use this n equals 100 to simulate 100 fake batting averages. So we're going to make a simulation using the uniform distribution. We're going to take random uniform distribution.
RUnif, not RUnif.
Yeah, RUnif.
I read that as RUnif.
I always do too. We're going to take the 100 random uniform distribution. So no, random meaning every one of these values has an even chance of being selected. And we're going to use the minimum batting average observed in 2014 as the lowest value, and the maximum value as being the maximum value observed for batting average in 2014. And we're going to take a random draw between those two values, and we produce this nice little vector of random values of batting averages. And those are going to feed into our simulation here. So we're going to run a simulation for every I in 1, 2 reps. Okay. So that's 1,000, right? We're going to build up this regression model by hand. So we're going to say Y is going to be the 2015 batting average, and we're predicting it from the coefficients of our model that we previously built. So we have beta naught, beta 1 multiplied by each of those 100 observations of run if batting averages that we produce. And we want to make sure that there's some jitter here, because again, it's not deterministic. There's a stochastic component. There's some error there. And so here we're going to basically create a vector of our norm. So we're using random normal draw from the data with a mean 0 and a standard deviation that is represented by the model error that we had before, which was about 2.7%. And so this is going to produce some random prediction, some random variance around those predictions. And then from there, the for loop is going to go through and it's going to specify a model saying, okay, how well did, if we built up this ordinary least squares model from our predictions and our X values of our run if batting averages, it's going to take those parameter estimates from that model and it's going to dump them into this matrix. And column 1 is going to be the slope, and column 2 is going to be column 1 is going to be the intercept, and column 2 is going to be the slope. And we're going to run this. This is going to run super fast. Done. Okay, so let's take a look.
1,000 players played.
Yeah, exactly.
1,100 players.
Yep. So we take ahead of that, and so now we have, okay, so what are we looking at? Each of these rows represents a different intercept and a different slope that could have come from the observed data that we had. So this is 100 rows or 1,000 rows of uncertainty around that red line that you see in the right. And so if we go back up to our script and we scroll down a little bit, right? So if we take the mean and we take the mean of the intercept and the mean of the slope, they resemble very closely the slope and intercept that we got from our model fit. And we can also express the uncertainty using quantiles. So this will be the 95th percentile interval. So 95% of the data is contained within the middle section here. And so there we see it's somewhere between 0.12 and 0.18 for the intercept, and 0.31 and 0.55 for the slope. And if we look at the original model output, we're pretty close to what we observed with the mean of column 1 and column 2. And the confidence intervals, these are the 95% confidence intervals, are going to be relatively close to what we observed right there. Yeah, so 11 point. So we see some of the uncertainty. And so now what can we do with this? We can do a number of things. Let's first plot the outputs. So if we run this, we're going to plot a histogram to evaluate or get a sense for what that uncertainty looks like around the red line being the mean of the intercept and the mean of the slope. We have all of these kind of random draws of potential slopes and intercepts that could have occurred given the data that we observed. Okay. The other thing we can do is,
still.
Yeah, you got it. The other thing we can do is we can plot the actual lines over the data. So here, what I'm doing is I'm saying, let's get a sense for, remember, we had a red line that represented one slope and intercept, the mean. But again, we have 1,000 potential slopes and intercepts. So what if we get a random sample of 10 slopes and intercepts, and we plot each one of those respectively? So first we plot our data. So we run this, and I think we got a little bit. Yeah, there we go.
Yeah.
There you go. You're right there. Yep. So cool. Okay, so that's the data that we were looking at. And now I'm going to use a for loop, and I'm going to say for I in 1 to length parameter rows. Remember, that's our random sample of 10. I want to produce.
Sorry, I was clearing out.
Yeah, there we go. I want to produce each of those 10 lines. So now instead of passing the model fit, I have to actually pass an A and a B, a slope and an intercept. So the slope is going to be in column 1 of those samples of 10 lines, and the intercept is going to be in column 1, and the slope is going to be in column 2. And so once we pass that into that for loop and we run it, we see 10 potential lines that could have been produced from this data. Okay. So if we were to plot our data in ggplot, and we use geom smooth, which we've done a billion times before, with method lm, we're getting a regression line and we're getting a standard error that's going to come up. And so that standard error, that confidence interval line is representing, I think we need parentheses maybe.
Is it theme minimal?
That confidence interval line is representing the uncertainty around the blue line. And we can actually show how this uncertainty is built up from our cool simulation that we built before. So if we go back over, we replot our data.
So this is the same data as before.
Same data. Now, instead of taking a random sample of 10 lines, I'm going to produce a sample of all of those lines.
Boom.
And plot them over the top. And then I can put the mean line in. And now we see the exact same plot. And we have an understanding of the uncertainty that was used to produce what we saw in ggplot. And now to finish this one up.
Lots of information.
Yeah, lots of info. To finish this one up, what can we do? This is the intro. We'll give a little intro here to base. If we have prior knowledge about the variability in year-to-year batting averages, we can go up to line 208. And here we've specified in our prediction, our regression prediction, we've specified this error that has a mean 0 and a standard deviation of 0.027, which came from our model. But what if we were like, you know what? We know from historic data, players really vary about, maybe 7% from year to year. Maybe we don't want to be so bullish because we only used players that had 250 at bats. Maybe we want to take into account more uncertainty. We can rerun this bad boy. We're going to get much larger amount of variability. And when we go down to here, we're going to see that now we have a much larger amount of uncertainty around our predictions than we did before. And so this is one of the ways that simulation is pretty cool, is we can change something within the simulation and get an appreciation for what it potentially could mean going forward if we were trying to make an estimate. Mm-hmm. And so I think today we'll probably leave it at that and pick up next time talking about resampling and more on simulation, and then we'll kind of get into Bayes.
All right. So yeah, that was a lot of information. Thanks, Patrick, for going through that and talking through that. I think it helped me kind of understand it a little bit more clearly. And I like the tie-in of Bayes there at the very end. So thank you all so much for joining us. As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And you can find me on Twitter at OSPPatrick, and Tidy Explained on Twitter at Tidy_Explained. And you can hit us up on Gmail, tidy.explained@gmail.com. You can open up an issue on the GitHub repo, or you can go to YouTube, like and subscribe, drop us a comment down there. We do have a Patreon page. We appreciate everybody who listens. And if you enjoy our work and you'd like to buy us a cup of coffee or a beer, we would gladly appreciate that as well.
Thank you all so much, and keep on exploring your world.